Now we're going to be analyzing another use of, explaining another use of IR spectroscopy, and this is to follow reaction. What are the changes in a chemical reaction? As we see here on the arrow, this is Jones reagent, strong oxidizing agent. When you do, you have sodium dichromate and sulfuric acid, you're making chromic acid in situ. And that's a powerful oxidizing agent. Primary alcohols oxidize first to aldehydes and continue to oxidize to the carboxylic acid. Now let's look at the changes. So now I have an alcohol, and in the product I have a carboxylic acid. So that should be a very broad signal in the region of the OH, and that will be this one. So it's very broad. The second option, this is more for the alcohol band, so it's not as broad as you can see, whereas for the carboxylic acid, it looks like very wide. And if this is 3000, it goes above that. As you can see, though that's a carboxylic acid shape, let's say, and this is more like alcohol type, the other, so not as broad. Then we will see, of course, the appearance of the carbonyl band. Well, this, I'm going to make this in another color. So the carbonyl group is at around 1700. So I expect that to happen. And that's essentially the changes that I see in that reaction. So I can monitor if my oxidation had taken place successfully by the appearance of the signal of the carboxylic acid, and the second band is the carbonyl group of the carboxylic acid. Let's do the second one. Now this is, we're going from an alkyne, and this is a partial hydrogenation using a Poisson catalyst, Lindlar, which always give you the cis alkene. So I'm going to add the two H's because this is the main change that I will see here. Carbonyl band, that's not going to change. You have it in the initial compound and in the final. What has changed is I had a triple bond, the alkyne, and now I have a double bond with two H's. So the main change here is the appearance of this signal above 3000, which is the stretching. This is a hydrogen attached to a carbon sp2. That is the alkene, what we see here. Okay. Now, this reaction is similar in the sense that it's a partial hydrogenation with a metal, sodium, and ammonia. And what is the change that you're observing here? You're adding this. Now, in principle, you will have, of course, the same change. You say, okay, I have a change in hybridization in these two carbons to now carbon sp2, and that stretch. That signal should be in the same region. Now, this compound, that is what we should be seeing. But now, what is interesting in this compound is that because the strands, and here you will have an R group, right, with an electron withdrawing. Point is that here we will have a zero dipole moment. That will affect mostly this band, but since this carbon-carbon double bond is in about the same region, this is at about 1600, and I don't see that listed here. In the case of the C's, it's probably seen, but here it will not be seen due to cancellation of the dipole moment. So that's a main change that I should be observing for this. Let's look at the next reaction. What are we looking at here is now a hydrogenation, and this is an alkene. But notice this alkene is tetra substituted. What it is that we don't have a hydrogen attached to a carbon sp2. So we don't have this. So this signal in 3100 will not be there. so not present. Instead, I'm simply adding H's here. But all of the other signals, this is carbon sp3 H's. And I have a number of those in the final molecule. So that's not listed here, but this is right under 3000. So say at about 2800 centimeters -1. And so, but I will not be seeing much changes in that area since I have a lot of carbon sp3 hybridized in the reactant and in the product. And so no major changes in here really, because the double bond carbon-carbon, which is in the reactant, the alkane, is at about 1600, but it's not as strong, and it's not listed here. What I have listed is the carbonyl stretch. So this is the carbonyl group, and it's present in the reactant and in the product. So according to what is in the list, I don't expect major changes on that. Because again, what you're introducing is hydrogen, and this stretch, but this is already, you have a number of signals in that area. Now let's look at another transformation, another chemical reaction, another oxidation. Here you are oxidizing an alcohol, a secondary alcohol, and secondary alcohols oxidize to the ketone regardless of the oxidizing agent. So what should I see if you're following the reaction? And if you do that at the lab, typically when we do synthesis, we take the IR of the reactant and then of the product to see if we're monitoring if we had the change that we want. So and what we see here in the reactant, yes, is the OH, and this is this bond brought here. So yes, that's the major thing. The other signals that I see just under 3000, those correspond to stretches of carbon sp3 hybridized hydrogen. That's the main thing. Everything else that we have is under 1500, so not significant. Significant band is then again the OH that we have here. Now in the product we have oxidized. What we should see is that the OH disappears, and that's the case. We don't have the OH band that we see here in blue. It would be like here, and it's not. So I'm gonna erase that. That's not there. Instead, I should have the appearance of a carbonyl band in about 1700, and this is it. So it's clear that this band was not present, this band of the carbonyl was not present in the reactant, and it is in the product, so very distinct change. Now, if you did an incomplete reaction, say that is impure with the alcohol, then the spectrum that you may see is actually can have bonds of both the reactant and the product. So if you see something like this, that means yes, you oxidize part of the alcohol, but it's still there's some alcohol remaining. That's what that will mean. But also you can follow reactions by TSC, and you can figure out whether the product is impure or not. Okay. One more reaction. Here we have, that is a hydrogenation of octene. So let's draw the structure of octene. So 1, 2, 3, 4, 5, 6, 7, 8. And it doesn't say what isomers, so I'm just going to put the double bond in 1, 2, 3. So 3 octene in this case. So I'm going to say 3 octene, but it doesn't matter much if it is in any other places. What is important is that we're doing this reaction while hydrogenating, which is that we're adding hydrogens across the double bond. So 1, 2, 3, 4, 5, 6, 7, 8. That's what we're getting. What is the change? Well, main change is what we have here. The stretch, that is a carbon sp2 hydrogen, which is right above 3000. This is how we said before. This is my about 3000 line when it came out, not straight, but it's okay. This is right above, so this stretching is at about 3100 centimeters -1. And in the alkane, we don't have that band, so essentially that's that. The other stretch that's interesting is the carbon-carbon double bond. That is the 1600, and this is the band that we see here. Notice that the peak at the band of CH carbon-carbon double bond stretch is not as intense as the carbon-oxygen double bond, because here the dipole moment of this is greater dipole moment, so this is more intense. Okay, so that's a change that we will see. Appearance of the band, this one right here, and this right here. These two are new. Last, let's analyze this reaction. There is a series of reactions, so I'm going to go over what's going on in each step. The first step here, it is we're going to be doing the halogenation of an alkene. So, because we don't have peroxides, that will happen Markovnikov, and not going into the mechanism, but the Markovnikov addition. So after reaction 1, in Markovnikov, you're going to add the H at the least substituted. So I'm going to put the H here, and the bromine at the more substituted. Because the reason for that is that when you add first the H at this carbon, you form a more stable carbocation. So, but directly I'm gonna do the product. So after I do the Markovnikov addition, I'm going to have a bromine right here. So that's step 1. How can I do to follow up that reaction? Well, we will see that in the reactant. I'm gonna erase these little things here. In the reactant, we have a hydrogen here. So I can follow up that because this is a stretch of a carbon sp2 hybridized, this one, H. And that stretch is at about 3100 centimeters -1. And that will not be present in the this product under here after I have done the hydrogenation. So step 2, reaction 2 here, what is essentially an E2 reaction. So here it is an elimination, and what we're doing is I have an H here, and here we will see, I'm going to just write this ethoxide potassium is just the counter ion. So I'm going to get this hydrogen, I'm going to form a double bond, and that will go. That way I'll be making this product. How can I monitor the change? Well, here I will have now a double bond. So I should see in this product, I wouldn't have the stretch that I have here. That is not the case because this is a tetra substituted alkene. I may see this, but not a big band because there is no significant dipole moment here in the alkene. But this signal is at about 1600 centimeters -1. So that's what I see from, say, molecule A to molecule B. And I can monitor the intermediate step, as I said, and say that this is my final step. What is the last reaction doing? That is an ozonolysis reaction. These are the 2 fragments. So what should I see in the product? Well, we're forming carbonyl compounds, ketone and another ketone. So I should see here the appearance of a band at about 1700 centimeters -1. So I can follow the completion of that reaction doing IR through the different steps and see if the reaction has been completed as desired.